Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone to part 2 of lecture 5 in ITDR2103. In today's session, we'll continue on the probability theory, and exactly we will cover two main subtopic, which is odds in favor and conditional probability. Alright, now let's start with odds in favor. When I speak about odds, I will be looking for the ratio success to failure. Alright, how we can do so? We will divide the favorable outcome, which is the event E, over the unfavorable outcome. And then we can find the success to failure of an event in an experiment. So if odds in favor of an event E are m to n, then sometimes we write this as m to n or m colon n. Okay, in order to understand the definition more, let's start to solve the following example. So suppose that a weighted coin such that the probability of getting head in this experiment is equal to 0.65. Alright, let E be the event that the top face is head. Now we want to find the odds of favor of getting head on this experiment. So the probability of E is equal to 0.65 and the probability of not E is equal to 1 minus probability of E, which is equal to 1 minus 0.65, and this is equal to 0.35. Now, in order to find the odd, we need just to divide probability of E over the probability of the non-occurrence of E. This is equal to 0.65 divided by 0.35. So by multiplying top and by 100, then we got as 65 over 35, and this is equal to 13 over 7. So the odds in favor of getting head in this experiment is equal to 13 to 7. Alright, let's suppose that the probability of winning the next basketball game is 0.48. Now, let's suppose E be the event that the next basketball will be won. We need to find the odds in favor. Now, to do so, I need to find the probability of E, which is equal to 0.48. And the probability of E, it is the probability of winning of the next basketball game. The probability of E complement, or we call as the unfavorable outcome, which is not winning the next basketball game, is equal to 1 minus 0.48, which is the probability of winning the next basketball game. And this is equal to 0.52. Now, in order to find the odds in favor, we just need to divide the probability of E over the probability of E complement or not E. So 0.48 divided by 0.52. This is equal to 48 divided by 52, and we got that the odds in favor is equal to 12 over 13, which is the odds in favor next basketball game are 12 to 13. Okay, let's suppose I've got the odds in favor of an event in an experiment which equal to 4 to 9. Then we need to find the probability of E. In order to do so, let's just recall our rule to find the odds in favor, which is the probability of E over the probability of not E. And this is equal to 4 to 9. Now we need to find the probability of E. So in order to do so, we first multiply both sides. So we got that 9 probability of E is equal to 4 probability of not E. All right. Then we want the probability of E in one side. So we will multiply by 1 over 9 again here. Now all these steps are mathematical steps. You've already got those information. So 9 will goes with 9, then we're left with probability of E equal to 4 over 9 multiplied by probability of E complement. Okay, so we already knew that in order to find the non-occurrence of an event, we just need to subtract the occurrence of the event by 1. So probability of E is equal to 4 over 9, 1 minus probability of E. Okay. Now we need just to multiply those two by 4 over 9. So we got here the probability of E equal to 4 over 9 minus 4 over 9 probability of E. All what we need to have is combine the similar from both sides. So we'll take this in here. So we got that 4 over 9 PE plus PE equal to 4 over 9. So by taking the common factor, we got that PE out, then 4 over 9 plus 1 equal to 4 over 9. All right, now we will add those together. So we got that probability of E is equal to 4 over 9, and here in order to add this one to those, we just need to multiply up and down by 9. So we got that 9 over 9 equal to 4 over 9. Adding together, give me that probability E, then 13 over 9 equal to 4 over 9. So in order to find the value of the probability of E, then we need just to multiply by 9 over 13 and again here. So 9 will go with 9 and here will goes together. Then we left with probability of E is equal to 4 over 13. And here we got the probability of an event is occurring in this experiment. Now, to avoid all those steps, we got a theorem here says that if E is an event that the odds in favor of E are m to n, then we can find it something like this. Then the probability of E is equal to m over m plus n, and the probability of not E is equal to n over m plus n. Here is an example. The odds in favor of winning a bingo game are 5 to 17. Now let E be the event of winning the bingo game. We need to find the probability of E. So in order to do so, we will just recall the past theorem, which says that the probability of E is equal to M plus N. What is M? What is N? From the theorem I got, the probability of E over the probability of E complement is equal to 5 over 70, which is equal to M over N, right? Yes. Then M here is equal to 5 and N is equal to 17. So the probability of E is equal to M, 5, and then 5 plus 17. It is equal 5 plus 17 is equal to 22. Yes. And for the E complement, it will be equal to 17 over 5 plus 17, which is equal to 17 over 22. Right. Now let's move to the second subtopic of our session, which is conditional probabilities. And in order to understand the conditional probabilities, let's just solve this problem. Then we will define what do we mean by conditional probabilities. So consider the throw of two distinct fair die. We want to find the probability of getting a sum of 7 when it's given that the digit in the first die is greater than that of the second. So here we need to find the probability I'm getting a sum of 7 when it's given that the digit in the first die is greater than the second die. But here in mind this keyword, given that, represent the conditional probability. So in order to solve this problem, first we need to find the number of possible outcomes in this experiment. So for the first die, I have 6 possible outcomes. For the second die, I've got also 6 possible outcomes. So the number of all possible outcomes of this experiment is equal to 6 times 6, which is 36. Now let E be the event of getting a sum of 7. So the possible outcomes from my sample space, if I add the first number of the first die and the second, I'm getting 7, is 2 and 5, 5 and 2, 3 and 4, 4 and 3, and 1 and 6, 6 and 1. Okay, now let F be the digit of the first die is greater than the digit of the second die. And here it can't be. The first die is greater than the second, so it might be 6-1, 6-2, 6-3, 6-4, and 6-5. Then we got 5-1, 5-2, 5 3 5 4, and then we got 4 1 4 2 4 3, and then 3 1 3 2, and finally 2 1. And those all the possible outcomes where the first number is greater than the second number. Okay, now from those what we got the possible outcomes, we can see that G is the event where sum of digits is 7 and the first digit is greater than the second digit. So it's something like G is the E intersect F. So let's go back to E and F. And here we got that E is getting the number 7, sum of 7, and F is the bigger than M. So the intersect between E and F is, you can see here, 5 and 2, and it is here. You can see 4 and 3, and it is here. And you can see 6 and 1, which is also here. So E intersect F is equal to 6 and 1, 5 and 2, 4 and 3. And here we got the G. Okay? Now, let us do it in another way. We can see that the number of possible outcomes in G is equal to 3. The number of possible outcome on F is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So here we got that the number of element of F is 15. Okay, and we already got that S is equal to 36. Okay, now first the probability of getting F, G over F, is equal to 3 over 15, which is equal to 1 over 5. The probability of F is equal to the number of elements on F over the number of elements on S. So here we got that F is equal 15 and S is equal 36, which is equal to 5 over 12. The probability of G is equal to the number of elements on G over the number of elements on S, which is equal to 3 over 36, and here we got 1 over 12. Okay, now from here, if we got the probability of G over the probability of F, it will be same as the probability of E intersect F over the probability of F, which is equal to 1 over 12 divided by 5 over 12, which is equal to 1 over 5. And if you notice, this one is equal to the one we got earlier. So from here, we can see that the probability of E given that F is equal to the probability of intersect over the probability of the first event happened. So here, the definition says that let E and F be two events in a sample space, then the conditional probability of E when it's given that the event F has occurred is written as follows. So the probability of E given that F, this happened first, then this should be happened. So this equal the intersect over the one happened first, which is F. An example here shows that E and F be an event in a sample space. If E is equal to 0.6, F is equal 0.7, and the intersect is equal 0.3. Then, in order to find the probability of E given that F, we can do what? We can just apply this rule. Okay, so here we got that probability of E given that F is equal to the probability of E intersect F over the probability of, which is equal to the intersect is 0.3 over F is 0.7, which equal to 3 over 7. As simple as this. Okay, let E and F be an event in a sample space, and suppose we got that the probability of E is 65, the probability of F is 75, and the probability of E in union F is 0.9. So we need to find the probability of E given that F. So the probability of E given that F is equal to probability of E intersect F over the probability of F. Now if you notice here, I've got the probability of F, but I don't have the probability of the intersect. So from where we can get the intersect is from the union here. All we know that the probability of E union F is equal to the probability of E plus the probability of F minus the intersect. All right. Now we got that the probability of union is equal to 0.9. The probability of E is 0.65. The probability of F is 0.75. And here is what we need to find. So adding those together give me 0.65 plus 0.75 is equal to 1.4 minus the probability of E intersect F. All right. Now in order to find the probability of E, we just need to take this out and put this inside. So here we got that the probability of E intersect F is equal to 1.4 minus 0.9. So here we got that the intersect is equal to 0.5. So we go back to our rule here. We got that the probability of E given that F is equal to intersect over F. And here, the intersect, we got it as 0.5, and F is equal to 0.75, which equal to 50 over 75. And this is equal to 2 over 3. And here we got the probability of E given that F. A theorem says that if E and F be an event in a sample space S such that F is not equal to 0, then adding the probability of E given that F to the probability of not E given that F is equal to 1. And here we got a new theorem we can apply to find the probability of E given that F. Okay, so let's suppose we got an urn contains 5 red, 6 brown, and 3 white marbles. 2 marbles without replacement are drawn. What is the probability that the second marble is brown given that the first marble is white? So let's say that let E be what the second event, which is the second marble is brown. Then let F be the event should occur first, which is the first marble is, where is it? Yeah, the first marble is white. Now, in order to find the probability of E given that F, I need first to get the probability of the intersect over the probability of F. So, first of all, in order to get the probability of F, I need to know the possible outcome in event F over the possible outcome of the whole experiment. Okay, now the possible outcome of F, which is the first marble is white, is I will take a marble twice. The first one, the only chances I got is the white marbles, which are 3. The second time I'm getting a marble, I will got how many chances? 5 plus 6 plus 3 minus 1, which is the one is already taken here. Okay, so 5 plus 6 plus 3 is equal to 14. 14 minus 1 is 13. The S, or the possible outcomes of the whole event, is equal to the first one, I'm getting the 14 marbles, 14 choices to be taken, one of them, and multiply by 13. So the probability of F is equal to 3 over 14. Now the probability of E intersect F, which represent the first marble, is white, and second is brown. So what do we mean by this? We mean that in the first, we mean that in the first time I need to get a white marble. So how many choices I've got? They are 3. In the second time I need to get a brown marbles, which how many choices I've got? They are 6. And over the S, which is my sample space. So it's equal to 14 over 13. And this is equal to, we will leave it as it is. Now, the probability of E, given that F, is equal to the probability of E intersect F over the probability of F, which is equal to 3 multiplied by 6 over 14 multiplied by 13. And here we got that the probability of F is 3 over 14. So we will eliminate the similarity here, and then we got that this is equal to 6 over 13. If we got En and F be the two events of an experiment where F is not equal to 0, so F should be occur, then the intersect is equal to F multiplied by E, the probability of E given that F. Also, this considered in finding the probability of E. A definition also says here, for an independent event of an experiment, if P a probability of F not equal to 0, then the probability of E given that F is equal to the probability of E. And also, if the probability of E does not equal 0, then the probability of F given that E equal to the probability of F. So for the independent event, which means there's no mutual events between E and F, no intersect. So here we say we have to exercise regularly. A survey of 100 students shows that 40% play basketball, 70% jog, and 82 are play either basketball or jog. So from here we need to show that if those two events are independent, then the conditional probability will be the same as the event itself. So here, let's say that donate the students who play okay, let J be the students who jog. So from here, we can see that the probability of the students who are playing basketball is equal to 40%, which is equal to 4 over 100, and this is 0.4. Yeah? Okay. The probability of students who jog is equal to 70%, which means 7 over 100, and this is equal to 0.70, and here 47. 0.7. Now, the probability of either playing basketball or jog is equal to 82%, which is equal to 82 over 100, and we got it as 0.82. Now, in order to check if they are independent, we need to find the conditional probability. So in order to do so, we need the intersect. So here we got that the probability of B union J is equal to the probability of B plus the probability of J minus the probability of B intersect J. So here we got that the union is equal to 0.82. Probability of students who are playing basketball is 0.4, and the probability of students who jog is 0.7, and we need to find the intersect. All right, then 0.82 is equal to, if we add 4 plus 7, then we got 1.1 minus probability of B intersect J. So as we did there, just swap those two, and we got that the probability of B intersect J is equal to 1.1 minus 0.82. And here we got that the intersect between basketball and jog is the probability, is equal to 0.28. Now, if we take the probability of students who are playing basketball multiplied by the probability of students playing jog, we will get that 0.4 multiplied by 0.7 is equal to 0.28. And from here, we can see that this is equal to this, which shows that those two events are B and J are independent. So we can also find the independency of two events in an experiment by following the follow steps. And here we reach the end of this session. Stay safe. We'll see you inshallah in the next session.